Greetings, this is Mark Anderson for Kellogg Community College, and today we're going to look at properties of graphs. Now, these are going to be some geometrical movements, and this is part one of a two-part video that's going to first of all focus on symmetries based on the x-axis, y-axis, and origin. We're going to then give a quick definition of even and odd functions, and then we're going to get into some very simple horizontal vertical translations. Alright, so we're going to first start off with the x-axis symmetry. The picture down below here that has x-axis symmetry is this first one. So I'm going to label this x-axis. I will also call this graph number 1 because as I do this worksheet, I'm going to be able to scroll down and look at more pictures, and I want to commonly refer back to this picture as picture number 1. So the x-axis symmetry, if you look at this point, and see if I actually could mentally fold this sideways parabola here. If I could fold that over the x-axis, it would fold perfectly onto itself. So the point in the first quadrant, x comma y, if I mapped it onto the point x comma negative y, it would then create a perfect symmetry around the x-axis. So this folds onto this folds onto this, every part folds onto itself, and vice versa. So this is when you can replace, y with negative y, you create an x-axis symmetry. The y-axis symmetry, which is located in this picture, which I will call picture number 3, this y-axis symmetry, you can see that in this case the x comma y in the first quadrant is getting mapped onto the second quadrant at negative x comma y. This is where we replace x with negative x. And finally we're going to deal with the origin, which origin symmetry is going to be graph number 2. And this is where the point in the first quadrant x comma y is mapped into the third quadrant as negative x negative y. So imagine me pulling this handle but doing it in a diagonal fashion where this would then map onto itself in the third quadrant. This is an example of origin symmetry where we're replacing x and y with negative x and negative y. Now if I look at some pictures here, let's call this pictures, even though this is Roman numerically labeled 1, 2, and 3, let's call this picture 4, 5, and 6. And now I'd like you to try to guess the symmetry. Does this have x-axis, y-axis, origin symmetry, or neither? Well, this one can get folded over the y-axis, so this one has y-axis symmetry. This has origin symmetry, because for every point x comma y, it can then get mapped onto negative x, negative y. And here, this is our x-axis symmetry. And that x-axis symmetry is because it folds over the x-axis. Now let's try graphs 7, 8, and 9. Now 7 would have y-axis symmetry because it can fold itself over the y-axis. Number 8, like number 5 above it, is origin symmetry. And number 9 is neither. It doesn't have any kind of symmetry, doesn't have origin symmetry, x-axis or y-axis symmetry at all. Now here's a little quick vocabulary. If you have an equation where the function of f of x is equal to x, f of negative x is equal to x, then you have something called an even function. Now, another way to look at it, if you this equation of putting a negative x in for my f of x and getting the same value as x, this is the same thing as having y-axis symmetry. Because y-axis symmetry replaces x with negative x. So if I can replace x with negative x, I now have y-axis symmetry, and we call these even functions. The even functions in this picture was number 3, 4, and 7. Now, equations that have f of negative x and are the same as negative f of x, these are considered as odd functions. These odd functions, another way to look at it, if I have a negative x and a negative y, then this would be origin symmetry. Origin symmetry would be problems in terms of the graphs up above. 2, 5, 8. 2, 5, and 8 are my odd functions in the problem. Now, if you're curious, like, well, what about the x-axis symmetry? And the reason why we don't talk about that is x-axis symmetry is not a function. Notice this is even functions, and functions have to pass the vertical line test, and then odd functions, they would also have to pass the vertical line test. Alright, so for our final thing we're going to learn today is translating or shifting graphs horizontally and vertically. First of all, we need the horizontal shift equation. If we're going to make a horizontal shift, we're going to have y equals f of x plus or minus c, because we're going to affect the variable x inside the parentheses, and if our c happens to be positive, we're going to shift this left that many units. And if our c happens to be a subtraction or a negative, we're going to shift it to the right. One of the common patterns that show up in algebra and geometry is any effect on the graph horizontally is usually opposite of what you think it's going to be. So positive numbers get left shift and negative numbers get right shift. But if we do a vertical shift, notice how we have to apply the letter C to the outside of the parenthesis. This is going to shift in the way that you think it's going to be. A positive C is going to be shifting up, and a minus C is going to be shifting down. So in this first equation where it says write an equation for a right horizontal shift of 2 units, this would be the equation y is equal to 4, x, and for a right horizontal shift, minus 2. Because a minus c, that constant to move or shift the equation, is going to be opposite of what you think it's going to be. So shifting it to the right is minus 2. So what I like to do is put a dot at every end and every bend. So at the ends and the bends of the line, we are going to move this to the right 2 units. It just so happens that every tick mark on this graph is 2 units, so moving it to the right 2 units is moving 1 tick mark. So there's where that movement's going to be, there's where this movement's going to be, and from this 4 to this 6, that's where that movement's going to be. And by connecting the new dots, I have now created a nice little check mark. Kind of reminds me of an Amiga logo from an old, it's one of my favorite old computers there. But let's go and keep looking at some other shifting here. Let's look at these two before we finish the video here. Alright, so write an equation for a vertical shift down 4 units. So here we have y equals f of x minus 4. And notice how the minus 4 was outside of this equation. Horizontal shifts are inside with the x, vertical is outside. So here I'm putting a dot at the ends and the bends, and I'm moving down 4 units, which happens to be 2 tick marks. So this dot would go from a height of 4 to a height of 0. This would go from a height of 0 to a height of negative 4. This one goes from a height or y of 6 down to a height of 2. So here's my new check mark, like so, which each of these to help translate it. So finally, writing an equation for a horizontal shift of right 4 units and a vertical translation down 2 units, this is going to be inside there, the horizontal shift to the right, so x minus 4. And a vertical translation down 2 units is going to be minus 2. So this means that each dot is going to be moved in 2 different directions before the end of this problem. So this is going to be moved 2 units down and 4 units to the right. Let's go to 4 units to the right first. So over here and then down. Oh, it's going to land right there. So there is my movement there. This is going to use 4 movements to the right and 2 down here. So I'm just doing a little dotted line where that's going. Now this one's at 4, so it would technically go to the 8 right there, and I know I don't have an 8, so let me just extend that and put 8 there. Okay, so 4 units to the right and then 2 down. Alright, so this is the new check mark right there. So it got moved 4 to the right and 2 down, 4 right and 2 down, 4 right and 2 down. And there's our first part of this 2-part video to talk about all the different kinds of patterns we can have with functions and all the cool translations and shifting we can do. The next video is going to talk about compression stretches and shrinking. It's going to be an interesting one, especially with with what we've learned so far today. Well, thank you very much for watching.